Hello everyone, I am Sumedha MR. We are the students of RVCE, RV College of Engineering. Aditya Kamarthi, Chirag S, Yashwant Kumar C are my teammates. We are done with the project based on the topic design and development of self-cleaning membranes for advanced treatment of wastewater. Uh, Coming to the introduction part, next slide. Membranes. Basically, membranes act as a barrier which allows some particles, ions, or some things to go through it. There are some types of membranes: biological membranes, synthetic membranes, etc. Membranes are we can carry so many processes through membranes. Membrane processes are classified based on their pore size, membrane pore size, like microfiltration, ultrafiltration, nanofiltration, etc. etc. Next slide. Coming to the main aspect, wastewater treatment. Um, Water is most living. In 100%, we have only 1% water ready to use. So that it is very important to it is important to do wastewater treatment to convert it into pure water or potable water. There are so many stages carried out in this process. The first stage is mechanical treatment. Um, In this in this stage, water flows through one screen, which filters out impurities like leaves, paper, textiles, etc. This removes around 20 to 30% impurities. This is done with mechanical treatment. Next, biological water treatment. After mechanical treatment, wastewater supplied to aeration tanks in which biological treatment takes place. This tank contains activated sludge in which oxygen supply will be there. Then microorganisms and bacteria present in activated sludge will convert the organic impurities into the inorganic impurities. So that this process is also called as activated sludge process. Next, chemical water treatment. Next slide. In this stage, many chemical processes are used so that the chemical properties required, like the acidity of the wastewater, neutralizing the acidity of the wastewater, reduction of the solubility of the water, etc. etc. Then, membrane process. This is the final step of wastewater treatment. The water passes through the membranes that filter even small particles, ion molecules through osmosis and reverse osmosis and other processes. The pollutants retained during filtration, nanofiltration, reverse osmosis, and many other membrane processes are filtered into sludge treatment. The water now reaches the last stage of the treatment. The treated water stored in a tank. After going through all these different techniques and processes, the water gets purified. Then this purified water can be used for different course. Next further, Chirag will explain.
Thank you, Sumedha. So for this membrane technology, the main hindrance is membrane fouling. Fouling is the undesirable buildup of organic and inorganic deposits on the membrane surface. Through these deposits, it diminishes the membrane's ability to filter the different contaminants. So foulants can be of different types like colloidal, biological, or organic. And when a membrane pore gets folded, then its flux will get severely reduced, and which indicates that very less water can travel through the membrane at a constant pressure. So fouling is classified into many types based on the strength of the particle adhesion to the membrane surface. Fouling can be broadly classified as reversible or and irreversible fouling. Using a strong shear force or backwashing, reversible fouling can be eliminated, but irreversible fouling cannot be easily eliminated. Reversible fouling will also can be converted into irreversible fouling by if a strong matrix of fouling layer forms with the solute during the continuous filtration process. So controlling of fouling becomes a important thing in this membrane technology. Although membrane fouling is an unavoidable part of membrane filtration, but we can reduce it to the maximum extent. We can reduce it through the processes like cleaning, membrane selection, and operating conditions. Membranes can be cleaned in a variety of ways, including physical, biological, and chemical methods. Coming to the self-cleaning membranes. Self-cleaning membranes can become the future in this membrane technology. Actually, the fouled membranes are not only a financial burden, but they are also a sustainability issue because the high pressure required to drive water through the clogged pores greatly increase the plant's energy consumption. Finding a simple and quick technique to solve this issue not only makes financial sense, but also makes sense for the environment. Self-cleaning membranes provides a vital answer to this fouling problem. Purification and treatment of water membranes that can quickly clean themselves when fouled could improve the energy efficiency of pressure driven membrane filtration systems. So, cleaning membranes manually becomes a hectic job. So, uh, upcoming days, the self cleaning membranes will surely be the future of membrane technology. So, coming to the literature survey, we have gone through many journals while making this project, but in this presentation, we mainly focus on three main journals which we have studied. Firstly, the membrane technologies in wastewater treatment. This journal was by Elam Obaito Izugbe and Sudesh Ratilal. So, coming to this journal, in the face of the water crisis, the world is trying to explore all the available options in order to decrease the over exploitation of the limited freshwater resources. One of the surest available water resources is the wastewater. As the population is growing rapidly, industrial, agricultural, and domestic activities are also increasing accordingly. Over the few years, the conventional wastewater treatment processes have succeeded to some extent in treating the effluents. Now, membrane technology has emerged as one of the favorite options for reclaiming the water from different wastewater streams. This journal looks at the trending membrane technologies in wastewater treatment, their advantages and also disadvantages. It also discusses about the topics like the membrane fouling, membrane cleaning, and also other membrane modules. There is an unending list of membrane technology applications in wastewater treatment. This journal attempts to summarize the major ones that are being used. So, the second main journal which we have gone through is the wastewater treatment using membrane technology. This was by Azile Ngonbi and Anele Pupa, Richard M. Moutlawley, and Philiswa N. Nomgongo. Water contamination by heavy metals, cyanides, and different dyes is increasing globally, and this needs to be addressed as this may lead to the water scarcity condition. Different techniques have been used to clean and renew the water for human consumption. Among those techniques, membrane technology is very promising to solve many problems. However, membrane fouling and membrane sensitivity to toxicity are the main limitations to this membrane technology. These ways include the incorporation of nanomaterials like graphene oxide and nanometer sized metal oxides. Overall, through this journey, it can be concluded that the membrane technology has been found to be a very promising method for the wastewater treatment when compared to all other prevailing conventional methods. This journal reviews about the recent developments in the membrane technology for the wastewater treatment, different types of membrane technologies, their properties, mechanisms, advantages, disadvantages, characteristics, and many more other features have been discussed through this journal. And the final main journal among all the journals which we have gone through is the design of advanced fouling resistant and self-cleaning membranes for treatment of oily and impaired water. And this journal was by the author Daniel Vandera. So through this journal, the overall abstract is to design and develop advanced anti-fouling and self-cleaning membranes for treatment of impaired water. Membranes offer many advantages over many of the conventional treatment methods, but membrane-based treatment processes for the oily water often fail due to the membrane fouling. Therefore, the most primitive objective is to design membranes that decrease the foulant accumulation and provide an easy chemical-free way to remove the attached foulants. So modifications are necessary for the surface of ultrafiltration membranes with polymer nanolayer coatings using methods that enable nanoscale control over the chemical and environmentally responsive conformational properties of grafted polymer layers. So this journal introduces a three-step surface modification procedure which was implemented to modify the commercial regenerated cellulose ultrafiltration membranes by grafting block copolymer nanolayers from the membrane surfaces by surface initiated atom transfer radical polymerization. After the successful demonstration of all these modification strategy, and these strategies were for preparing fouling resistance, easily cleanable ultrafiltration membranes for water treatment. At last, this journal focuses towards a better understanding of the role of polymer nanolayer structure. And finally, this research work indicates that well-designed and modified ultrafiltration membranes can be used to separate organics from large volumes of impaired waters at a high flux. So this is about the literature survey which we have done. Next, my friend Yashwant will continue the materials and methodologies of our topic.
For the methodology, we have spray-assisted non-solvent induced phase separation, SANEPS, which is an approach for fabricating superhydrophobic PVDF membranes, that is polyvinylidene fluoride membranes. This method is used to alter the phase inversion speed and crystallization growth rate to manipulate the shape of semicrystalline polymer membranes. The approach uses water as the sole coagulation medium and does not require any further treatment. Here, we describe how to use the SANEPS approach to create superhydrophobic self-cleaning PVDF membranes with high porosities and configurable multi-level roughness. The spraying step causes not only quick partial surface solidification but also local membrane surface deformation, resulting in the first level roughness. When the nascent membrane is introduced into water coagulant, the newly produced skin will obstruct the solvent-non-solvent exchange, causing delayed demixing and the development of second level of roughness. Further, various spraying materials can be used to adjust membrane morphological structures. Air and ethanol, for example, have low surface tensions and solubility parameters, resulting in hierarchical colloidal formations. Water, a powerful non-solvent with a high surface tension on the other hand, aids the creation of volcano-like humps in an open network structure. The SANEPS PVDF membranes demonstrate exceptional repellence towards many types of aqueous solutions without any additional surface modification and show remarkable flux salt rejection and long-term stability in treating feed solutions containing 10% sodium chloride and 2000 ppm Bengal rose red stain. Further, the SANEPS approach has been discovered to be easily adaptable to various semicrystalline polymers in order to considerably increase their inherent hydrophobicity or hydrophilicity by increasing surface roughness and porosity. Finally, employing widely accessible semicrystalline polymeric materials such as HFP or hexafluoropropylene and PAN polyacrylonitrile, the SANEPS approach has been verified for fabricating highly porous and hierarchical surface architecture. The materials used in this approach is the following: PVDF homopolymer, uh, Kynar HSV 900 for example, PVDF HFP copolymer such as Kynar Flex 2801, PAN, NMP or N-methyl 2-pyroolidone which is used as a solvent, ethylene glycol used as non-solvent, sodium chloride, ethanol, graphene oxide solution, sodium dodecyl sulfate, and deionized water. On to the next slide, we have membrane preparation. Um, so to make a transparent polymer blend, we use the homopolymer, the solvent and the non-solvent, and combined in a round bottom flask and stirred at 60 degrees Celsius overnight. Glycol here functions as a pore former to improve membrane porosity, and non-solvent disturbs the dope system's equilibrium and causes polymer precipitation. To remove air bubbles, the polymer solution is settled at 60 degrees Celsius for 12 hours. As shown in the figure, flat sheet polymer membranes are created. First, a casting knife with a height of 200 meters is used to cast the polymer solution onto a glass plate. The nascent membrane is then sprayed with compressed air or a specified solution for 30 seconds using an airbrush with a 0.3 millimeter nozzle size. To guarantee that the spraying is consistent, the air gun is moved over the glass plate at a constant speed of 5 cm per second. If a liquid phase spraying substance is used, the membrane should be sprayed with compressed air for extra 5 seconds to help the liquid solution evaporate faster. The airbrush is then coupled to an air compressor that generates a 2 bar operating pressure and a 20 to 23 liter per minute airflow rate, and the surrounding temperature is maintained at 25 degrees Celsius. The membrane is then immersed in deionized water for 20 hours to complete phase inversion and then dried in a freeze dryer for further use. The membranes thus obtained are referred to as SANEPS PVDF membranes. A control membrane without spraying treatment may also be prepared for comparison by using the NIPS method, where the newly cast membrane is directly submerged in the coagulation bath of deionized water for phase inversion. On to the next slide. Uh, we'll look into another method which focuses on modification of ultrafiltration membranes for treatment of produced water. Surface modification of regenerated cellulose ultrafiltration membranes is achieved via polymerization of block copolymer nanolayers on the membrane surfaces. However, we can minimize foulant buildup on these membranes and provide a simple chemical-free approach to remove any attached foulants by managing both the chemical and environmentally responsive structural features of these polymer layers at the nanoscale. Membranes are generally altered by grafting poly-N-isopropyl acrylamide, that is PNIPAAM in short, block oligoethylene glycol methacrylate (PPEGMA) nanolayers onto the surface. At 32 degrees Celsius, PNIPAM has a lower critical solution temperature. The chains hydrate below this temperature to create a random coil shape but collapse above the temperature to produce a smaller structure. This is commonly used to build temperature responsive materials, including several instances with membranes, because its physical and chemical properties can be easily controlled by changing the temperature. As a result, membrane surfaces were grafted with this to make them temperature responsive. To increase the antifouling properties of this modified membrane, PPEGMA is grafted as a second block. The dramatic reduction of flux to unacceptable levels as a result of alteration of the membrane was one of the key issues discovered. By switching to a more open ultrafiltration based membrane, the following method can be employed to solve that problem. The surface of these ultrafiltration membranes has been modified to provide responsive chemistry while maintaining high flux. Water quality versus permeate flux can be optimized by using a more open membrane. For this approach, uh, we use ultrafiltration membranes such as hydrosalt, polyethylene glycol methacrylate, that is PEGMA macromonomer, and N-isopropyl acrylamide. We use AIBN, benzene, and the following compounds. Uh, Next, onto the next slide. From membrane modification, the three-step technique for surface initiated polymerization to modify a regenerated cellulose membrane with PNI-PPAM block PPEGMA is depicted in the figure aside. Um, Surface initiated polymerization is done to graft PNI-PPAM chains from the inhibitor groups after initiated molecules of the polymerizer were bound to the membrane. Reinitiation of these chains is then followed by grafting PPEGMA as the second polymer block. The membranes are then submerged in methanol for 15 minutes to remove glycerin, which is employed as a structural preservative for these membranes. They are then washed completely with water to remove the methanol, and finally they are equilibrated with tetrahydrofuran. Membranes are later taken from the tetrahydrofuran and placed in the glove box after being dried with a stream of nitrogen. The membranes are taken out from the solution after membrane activation and rinsed completely before storing them in tetrahydrofuran until polymerization. Polymerization of PNI-PPAM is carried for 1 hour at atmospheric temperature. The obtained membranes are removed from the solution and extensively washed with methanol and water and stored in methanol. The above procedure is repeated for PPE-GMA, and polymerization is carried out at the same temperature for 3 hours. An hour of PNI-PPAM polymerization yields a layer thickness of about 54 nanometers, while a 3-hour PPE-GMA polymerization yields a layer thickness of about 2 nanometers. Thereby, the modified membranes are carefully taken out from the polymer solution, washed with methanol and water, and stored in deionized water. Next, on to the results and discussion.
Coming to the results and discussion, after looking into the first method, we can say that this results in the introduction of SANIP's method to develop super hydrophobic and self-cleaning PVDF membranes as highlighted in the methodology part. Adding to these points, this SANIP's method can be readily generalized to other semicrystalline polymers to significantly amplify their inherent hydrophobicity or hydrophilicity by increasing the roughness of the surface and its porosity. The SANIPS approach offers a free and cost-efficient way of developing porous membranes with super wettability after treatment. In comparison to traditional NIPS and VIPS approaches, however, extra freedoms are introduced in the membrane manufacturing process using SANIPS. Unlike in NIPS and VIPS methods, where the non-solvent takes either liquid or vapor form, the spraying materials in SANIPS method can be in the form of gas, liquid mixture, or solid suspensions. On to the next slide. We have the conclusion. Membrane science and technology has experienced a long historical development in laboratory study before realizing its first important industrial application in the 1960s. With nearly 60 years of rapid advancement in the membrane technology, today membrane-based processes occupy numerous industrial applications and have brought great benefits for the improvement of human life. Membrane technology has proven to be a more favorable option for wastewater treatment plants nowadays. Although membrane technologies are not a new invention to the mankind, but the varying nature and complexity of wastewater creates opportunity and necessity for more improvements in this area. Membrane filtration technology is nowadays rapidly becoming accepted in the wastewater treatment industries. As one of the important separation technologies, membrane separation has been widely used in many fields. The advantages of membrane technology include membrane processes and often do not require any phase change, which reduces the energy requirement. There are many more advantages for this technology. It has some disadvantages like fouling of the membrane, temperature limitations, etc. It is one of the important development directions. On to the next slide. We have the future scope. Nowadays, the research works in the field of membrane technology are increasing rapidly. Research into the use of membrane-based processes in the industrial sector is an interesting area for the modern membrane science and technology. There are some well-organized and promising aspects of membrane usage in the industries with the main focus on the energy conversion, environmental pollution reduction, and also process intensification in this broad field. Increase in the number of researches being done on membrane technology indicates that membranes definitely will become another alternative for the industrial processes in wastewater treatment. However, much research and development efforts are needed in order to commercialize the membranes in the international market. With the increase in the worldwide competitiveness in production, this has forced industries to improve the current ongoing process designs and also increase the importance of the natural environment. This has compelled the industries to develop new membrane process designs in the field of wastewater treatment. Next slide. This is all we had to say. and our research project has come to an end. Thank you.